And welcome to Calculus 2. We're going to continue talking about improper integrals. This time we're going to talk about improper integrals of type 2. So here's the definition. These are integrals that have a discontinuity somewhere in their integration interval, so between a and b, including possibly a or b. It could be an infinite discontinuity, it could just be a regular discontinuity, but if your function is continuous except at a, it has its discontinuity at its bottom limit of integration, then we set this up. Another limit as c approaches a from the right at the bottom. So you'll just do a limit as it approaches the questionable value. And again, if that exists, then that's the answer. If the limit doesn't exist, we say the integral is divergent. And they have a similar thing for the upper limit. Again, you just replace it with a placeholder and then take that placeholder towards b, this time from the left because it's the right endpoint. And of course, if you have it somewhere in the middle, then you have to split your integral at that point, at your discontinuity, and evaluate both integrals, using limits for both of them. So that's what we're going to do. Improper integrals of type 2. It's going to be somewhat similar to what we were doing with improper integrals of type 1. It's just, instead of infinite limits of integration, we're just going to have points where your function is discontinuous. We're still going to do limits though, so it's going to be very similar. And here's our first problem. We're going to be looking at section 8.8, problem 25. This is on page 513. Going to evaluate the integral. This is x ln of x. I could try a simple substitution, but if I say let u equal ln of x, I'll get du is 1 over x. But I don't have a 1 over x, so I think I would just end up with an x squared, which would make it more difficult to integrate. But I think we can do this with a integration by parts, because we've done that kind of thing before. By doing integration by parts, we would let u equal ln of x, because that one will get simpler if we take its derivative. 1 over x dx. And then dv would just be x. So that'll get us v is 1/2 x squared. So then this becomes, remember, uv minus the integral of v du. So u times v is 1/2 x squared ln of x minus the integral of 1/2 x squared. Du is right there, so 1 over x dx. So that's just going to be minus the integral of 1/2 x dx, which is just going to be 1/4 x squared. So you got 1/2 x squared ln of x, 0 to 1. Now, 1 is the not 1. 0 is the problem here, because natural log is undefined there. So we're actually doing this, the limit as c approaches 1. Let's see, that would be from the left of, let's do a little bit of factoring out here. 0 to c. Let's see, I can pull a 1/4 out. Might as well pull that out here. 1/4. That'll get me, and I can pull an x squared out in here. X squared times 2 ln of x minus 1. Alright, if I plug in... I put that in the wrong place, didn't I? Dagnabbit. 1 is the issue, is fine, and c is the problem. I mean, 0 is the problem, so c approaches 0 from the right. Can't even pay attention to my own work. Alright, so 1 I don't think will be a problem. If you plug in 1, you'll get 0 here, negative 1 here, times 1, so 1/4 limit. I might as well distribute the limit as well. If I do that, it's not going to have any effect on that, so I will just get negative 1, and then minus the limit as c goes to 0 from the right, of 2 ln of c minus 1. Oh, and I forgot my c squared. I can probably do that a little bit better. Of c squared, 2 ln of c minus 1. Well, as c goes to 0, this would go to 0. This, though, would go to negative infinity. So that's the real question. And honestly, we can ignore the 1. So now we're looking at, we've got to figure out what happens as c goes to 0 from the right, to c squared 2 ln of c. Because I can multiply the c squared times the 1, and that goes to 0. Well, this is a limit problem. You have to figure out whether c goes to 0 faster than ln of c goes to infinity. If you know anything about ln of c, you might actually have the answer to that already. But an easy way to do it is using L'Hopital's rule and doing this. Because this is 2 ln of c over 1 over c squared. That's equivalent algebraically. Well, you can use L'Hopital's rule now because it's indeterminate. Top goes to negative infinity, bottom goes to positive infinity. You do L'Hopital's rule, you're going to get 2 times 1 over c over, let's see, c to the negative 2, you take its derivative, you get negative 2 times 1 over c cubed. Limit as c goes to 0. Right? And that's just going to get us, let's see, this c cubed will come around top, cancel out, you get c squared, negative 2 and negative, so that's a negative. C goes to 0 from the right of negative c squared. Negative doesn't really matter though, because c goes to 0, so this whole thing just goes to 0. So that does converge then. Negative 1 times 1/4 is negative 1/4. And there's the integral. Took us a little bit to evaluate this part because of the non-obvious nature of what the limit was going to be. But we got there. Let's do another one. I picked this one because the discontinuity is at 1, which is right in the middle of the interval. Because of that, we're going to have to split our integral. But if you look here, because of this absolute value, we'd have to split it anyway to evaluate it, because it has different formulas on both sides of 1. So if we look at the integral from 0 to 1, everywhere on that interval, the inside of this is going to be negative, so the root, the absolute value, would flip the sign. Negative of x minus 1. So that would be integral 0 to 1 of dx over the square root of 1 minus x. And then the other part is no problem at all, because 1 to 2, that's already the inside of the absolute value is always positive on 1 to 2, so the absolute value does nothing. So we're looking at dx over square root of x minus 1 two integrals here. 1 to 2 dx over square root x minus 1. As far as the integration, shouldn't be too hard. Here, if you let u be the inside, du is just dx, so it's just like integrating 1 over square root x, which should get me 1 to 2. I still really have to consider the problem of this side, but I'll ignore that for just a second. Let's see, if you take x to the negative 1/2, you integrate it, you get positive 1/2, and divide by it, you get 2. So 2 square root of x minus 1. Alright, here, 0 to 1. Here, if I let u be the inside, let's actually work this one out just so I don't mess up my signs. So du is negative dx. So we'll get a negative. And the integration, though, at that point, since it's still du over u, would be the same. So I'd still get 2 square root 1 minus x. It's just now we have to consider the other pieces. So I have to consider the limit as c goes to 1 from the left of square root 1 minus c. And I guess I need a negative there. Plus, when I plug in 0, I just get 2 square root of 1. Plus, no problem to plug in the 2. 2 square root of 1 minus the limit as c goes to 1 from the right of square root of c minus 1. I probably should have used a different letter for my limits here, but it's still pretty descriptive. In any case, neither of these limits are particularly difficult to evaluate now, since they're not indeterminate anymore. You plug in 1, that goes to 0. You plug in 1, that goes to 0. So we're just looking at 2 plus 2 equals 4. That's going to be it for this video. For the last video from 8.8, we're going to look at convergence and divergence. Some integrals we might not necessarily be able to integrate, but we can still talk about whether they are convergent or divergent using some simple tests. They're called comparison tests generally. We'll look at those next time, and we'll look at doing some examples as well.